we're going to learn how to calculate the enthalpy of a reaction, but we're going to use Hess's law in conjunction with the enthalpy of formation reactions and a new equation. But before we learn how to use the equation, I want to show you that the equation is just another version of Hess's law. The equation that we're going to use is the enthalpy of a reaction at standard states can be calculated by taking the summation of the moles of each product times the enthalpy of formation of that product at standard states, which you'll find in the back of a book or a textbook, maybe in the chapter 2. You're going to do that for every product and sum it up, and then you're going to subtract it from the summation of all the moles of each reactant times the enthalpy of formation of that reactant at standard states. Now, this equation is just derived from Hess's law. So the first thing I'm going to do in this video is I'm going to show you why this equation is just another version of Hess's law, use it again to prove that fact, and then have you use this equation and see it really is a shortcut with the reaction that I'm going to have you do at the end of the video. All right, so enthalpy of formation reactions are when we have 1 mole of a compound formed from its constituent elements. So the reaction that I want to study at standard states, and which means 298 and 1 atm, is this reaction. And it's not a formation reaction. It's calcium carbide solid reacting with water. So right away, this can't be a formation reaction, but we're going to use formation reactions to calculate the enthalpy of it. And then we're going to produce calcium hydroxide, which is a solid, it's a precipitate, and acetylene gas. We still have to balance this equation, which would need, you need a 2 there, and then there will be 1s. We will need those because those will be the moles that we're going to use up in this equation, and then these will come from a table. But I want to calculate the enthalpy of this reaction using Hess's law. I like to cover Hess's law first, and then this enthalpy of formation equation second, so you kind of appreciate it. All right, so what I need to do now is I need to treat this as like my goal equation. And then what I need to do is have other equations that are like steps that will help me get this equation and then add up those enthalpies and get the answer. Okay, so get that what that question mark means. So here is what we're going to do next. I'm going to get rid of these two first. So 298 and 1 atm. So we have to be at standard states. Just want to fill that up. Looks nice. What I want to do is write enthalpy of formation reactions for each reactant and product and then use them like Hess's law to calculate this overall equation. So that means I'm going to have to start with pure calcium and pure carbon, which are the constituent elements, again, up here, that make calcium carbide. And we want to make 1 mole of it. So that's why I've already kind of put a 1 right there. That means I'm going to need 2 moles of carbon, 1 mole of calcium to make this. Now, the value that I'm going to find right here is in that table in the back of the book, which would be what's going to go in those places if we were to use this equation. But again, I want us to use Hess's law first, even as a great review. Next, we're going to want to make water. So we're going to have to use diatomic hydrogen because that is its standard state, and diatomic oxygen. Now, we want to have this be 1 mole of water, so I have to use 1/2 here. And fractions are your friend. You can use them, especially in enthalpy of formation reactions. And 1 mole of hydrogen. So we're going to get our water. Next, we want to make calcium hydroxide. So the elements that would make calcium hydroxide are calcium, diatomic oxygen, diatomic hydrogen. And what's kind of nice with this one is 1 calcium, 2 oxygen, 2 hydrogen, and these are all 1s. That's fantastic. All right, last but not least, what if we wanted to make acetylene from its constituent elements? We need carbon and diatomic hydrogens. Great review of your diatomics here. And we're going to need 2 carbon, 1 mole of hydrogen. We're going to get 1 mole of acetylene. Okay, so then where do these values come from? Because if I'm going to use Hess's law, I'm still going to need them. So if I want to treat this as reaction, 1, 2, 3, and 4, I still have to have those values. So I'm going to go and look them up, and then at the back of the book or in your chapter, I pulled out the numbers that we're going to need for the reaction that I'm going to do and the one that you're going to do, plus a couple extra. So you need to go find the enthalpy of formation. Don't worry about the S and the G. Those are other thermodynamic data, entropy, and Gibbs free energy, and you don't need them now. So just ignore those. You want to find your enthalpy of formation. And I want you to see that this is the value that would go off to the side, just like any reaction. So it's a formation reaction, which is a synthesis reaction. And it releases 63 kilojoules, or it's negative 63. Next, states of matter matter. For water, I want to use liquid water. So I need the 286, not the 242. So states of matter matter, and you need to get the right one. And a separate thing, you could think about, why is this one less and why is this more exothermic? All right, so then what about for calcium hydroxide? It's very exothermic, 987. And then for acetylene being formed, it's an endothermic reaction. So some are endothermic and some are exothermic. That's also something great to see by writing all these enthalpy of formation reactions. Okay, next, for you, when you do your reaction, look at pick the right chemical. Also, pure elements in their standard states are 0, so that's kind of fantastic. And then I want to throw in something like ozone, because ozone is not a standard state for oxygen, and so it would have its own enthalpy of formation. Okay, all right, let's go back to Hess's law then. Hess's law, we want our reactants on the right side, so it's not. This is a product, and I want it here. So you would reverse this equation. And when you reverse this equation, you'd reverse the sign. So I'm going to rewrite them in a second, but I'm just going to kind of put in pink here, my plan here. Call it a pink plan. Okay, so then we want water also on a reactant side. So we're going to need to reverse this one also. And that would mean I would change the sign to be endothermic. All right, the next thing is your calcium hydroxide and acetylene are products, so they're on the right side. All right, so what I'm going to do, and now I would recommend that you rewrite these unless you have, a device where you can just erase easily, but I would carry these down and I would rewrite them. To save room on my space here, I'm just going to erase them and then put them on the opposite sides, okay? So that means I want calcium carbide here on the reactant side, and then I want the 2 carbon and 1 calcium. I just kind of wrote them in a different order, but that's still fine, okay? And then instead of this being pink or purple or whatever, I'm going to make this a plus, okay? So then I've rewrote that equation. Next, I need to rewrite this one also. I need to have my hydrogen and my oxygen as the products and my water as the reactant. So you'd put H2O on this side, and then you'll have your hydrogen gas and your oxygen gas. And then I need to erase, and I'm going to make this a plus, okay? All right, so the next thing I have to look at is, are my mole amounts correct? Okay, so I have 1, 2, 1, 1. So this was a 1, I just didn't write it. And right now this is a 1. So that's not what I want. I want to have this still be balanced. So I need to have 2. So the next thing you'll do is you need to multiply this whole reaction, including its enthalpy, by 2. So I need to multiply the 286 times 2. And I need to multiply each coefficient or each mole amount by 2. So I'm just going to erase again. This is where I would rewrite this if I were you. So you have 2, and then this one is a 2. So this one we reversed and we flipped it. Or sorry, reversed and we multiplied it. So we're going to take 1/2 times 2, which is 1. And then 2 times 286 is, in fact, I'm just going to leave that. I'm going to leave that so I remember to do that and show it below, okay? So then the last thing we want to do is check that this really removes all the reactants or products that are not part of the goal equation, okay? And it keeps the ones that are. So here we go. So we got 2 carbon as a product, and if you take more chemistry and learn about kinetics, we'll talk about what this is later. The next thing is 2 hydrogen, so I have 1 and then 2, so I do have 2 total. I actually really liked Hess's law the first time I learned it, so maybe you do too. But it could be why I'm a chemist. So we have 1 oxygen here and 1 oxygen here. It feels a little bit like memory match. And they have 1 calcium, 1 calcium. So that has removed everything that is not part of the goal equation, and it has kept the right amounts of each one of my reactants and products. So then the end goal is you just take all of these enthalpies and you add them up. Now I'm going to go to the bottom of this page and show you how this is the same, finally, as if I were to use that equation. Okay, so let me slide down to the bottom. Hopefully I got a pretty good memory here. So I had 63 kilojoules, and it's per mole, and then we added that to 2 times 286 kilojoules per mole. And then it was negative 987. I'll check in a second, but I'm pretty sure these are the right numbers. And the last but not least is 227 kilojoules, okay? So then again, the answer here is that question mark. The answer is this enthalpy of reaction at standard states for my calcium carbide reacting with water. All right, so let me just check the numbers. So 987 and 2, okay, perfect. So if you check on your calculator, you should get negative 125 kilojoules, okay? So that means way, way, way up at the top here, that is this question mark. I don't have room to write it, so I'm just going to assume that you would know to put it off to the side like that, okay? So that's that reaction. It is exothermic, and it gives off, releases or gives off negative 125. Okay, so the equation, here we go. What if we just would have used that equation from the get-go? So I'm trying to show you that this is just a derivation and it's a quick shortcut. Here we go. So don't forget, the product was first. So it's 1 mole of our product, which was calcium hydroxide, and then multiplied by its enthalpy of formation, which was negative 987 kilojoules for every 1 mole. Okay. Then I had to do the other product, which was 1 mole of the acetylene gas, multiplied by its enthalpy of formation, which was 227 kilojoules per mole. Now, I had to add that up and sum it, okay? Then I have to subtract that from, usually you run out of room with this one, so don't be surprised if you have the same problem. You got to subtract it from the moles of the reactant. So remember, it was 1 mole of our calcium carbide, and we're going to multiply that by, the calcium carbide was negative 63 kilojoules per mole. And then we have to add that to 2 moles of our water. And then it's going to be, remember it was negative 286. Just going to fit it here. Barely. Okay. Now take a look at the numbers. Do you see how it's got a negative? And you have a minus there, plus, plus. And what happens when you have a minus and a minus? Well, they cancel and they negate each other, sort of, and you end up with a plus. And then same thing here. This is going to be carried through here. So really, we have the exact same answer, but look how much faster it is. But I will be honest, a lot of students can do this equation. They learn how to do this equation, but they don't really understand that it's just another version of Hess's law. It's just a shortcut, because again, look how short that was compared to me writing all those formation equations, canceling them out, doing all the reversing and multiplying, etc. Okay, it's your turn now. You had a reaction, or I want you to do this reaction, where what if I burned acetylene? Maybe I didn't even tell you yet. What if you took your acetylene and you combusted it in air? So what does that mean? So if I want to do a combustion of acetylene, which is kind of the second reaction after you do the first reaction there. So this is your example. And I'm not going to give you the answer, actually. You're going to have to do this one on your own. It means that you're going to burn it in air, which is adding oxygen diatomic. And then I'm going to give you a little wait time. What do you make when you combust something in air? That's a hydrocarbon. You get CO2 and water, only if it's a hydrocarbon, though, okay? I'm going to have you balance this, okay? And what we're trying to do is we're trying to find the enthalpy of this reaction. Now, because it's a combustion reaction, a lot of people would say, what's the enthalpy of this? It's called the COM. Enthalpy of combustion. That's what I need you to find. Now, what I would like you to do is use that equation, make it short, use the values that I have up here, okay, right there, and calculate the enthalpy of combustion. Please, make a prediction first. You think it's going to be endothermic or exothermic if it's a combustion? And what do you think about the value? Do you think it might be a little larger than the first reaction comparatively or not? And then don't forget to balance this first, because again, you're going to need those way, way, way back up here. Those are your correct mole amounts, and then these you get off the table. All right, great job, chemists. I hope you enjoyed this video, and you can like, subscribe, or comment. And I hope you enjoyed doing Hess's law problems and enthalpy of formation problems like I do. In fact, I even bought myself a necklace that has this summation sign. Good luck, chemists. Hope to see you back or hear you back again on my channel.